Hello again, ladies and gentlemen. I have an opener for you. So my suggestion is to hit pause, try and work this out, and then compare it with the solution that I worked through. Okay, today we're going to be talking about Rolles' theorem and the mean value theorem. And this is the last section in the first chapter, and then I'll assign some review problems a little later on during the week. But you should have this completed by Friday. Okay, find the equation of the tangent line to this function, the quadratic, at the point in the interval -1 to 2, where the instantaneous rate of change is equal to the average rate of change over that closed interval from -1 to 2. Now, this is one that you probably want to read it a couple times and think about what it's saying. So there's two important phrases. There's the average rate of change, which just means slope, basically. And then there's the instantaneous rate of change. And the interval that we're dealing with is from -1 to 2. Okay, so let's start with average rate of change. Average rate of change. So at -1, there's the point on our graph, and at +2, there's the point on our graph. So the average rate of change is just the slope between those 2 points. So that's going to be f of 2 minus f of -1 over 2 minus -1. And let's see, f of 2 is 0. I'm just plugging it into the function here. And f of -1 would be 1 plus 2 is 3. And, oops, I was thinking ahead there. 2 minus -1, that's the difference of my x values from -1 to 2. And then we get 3 on the bottom, so that gives us -1. That's our average rate of change. Alright, the instantaneous rate of change, well, we know that means the derivative. So our derivative, f prime of x, is equal to 2x minus 2. So we want to know for what x value is the derivative equal to that average rate of change. So we're just going to set 2x minus 2 equal to -1. Add 2 to both sides, and we get a +1. And that gives us x equals 1/2. So at x equals 1/2, which is right about here on my curve, the instantaneous rate of change, which is the slope of the tangent line, equals the average rate of change. And as you can see from even a rough drawing, that those do seem to look like they're parallel. So let's reread this, find the equation of the tangent line. Okay, so we need to get the equation of this green line. We know the x value is 1/2. We need to find the y value. So we need to do f of 1/2, not f prime of 1/2. We know f prime of 1/2 equals -1. So the function value at 1/2 is going to equal 1/4 minus 1, so that's -3/4. I'm just plugging this back into f of x. So here's our y value. So we have the point, which is 1/2 comma -3/4, and we have the slope, which is -1. So now we can write the equation of the tangent line for our final answer. So that's going to be y minus a -3/4. So y plus 3/4 equals our slope, -1, times x minus 1/2. If you want to put that in a different form, great. No need though. There we go. Okay, so we're going to look at a couple of theorems now and see how we do with this. So the first theorem to understand, which is kind of the basis, if we wanted to do a proof-based calculus course, we would go through all the proofs on this. But there's one theorem that says if a function is differentiable at x equal a, which means it has a derivative at x equal a, then the function is going to be continuous at x equals a. And that should seem pretty obvious. Then we have a lemma, which is kind of like a theorem, not quite as strong. And it says, suppose that a function assumes either its maximum or its minimum on a closed interval AB, and we have some point C that's between A and B. If the derivative at C exists, then that has to be 0. So if you just try and draw an example of these, so we have some function f, we have an interval from A to B. If our function f assumes either a max or min on that interval, so let's say it's hanging out going like this, and it goes back like that. Here's f. It does have a minimum right here, so that's going to be c. Then f prime of c, if it exists, is 0. Now if that came to a sharp point, like maybe an absolute value graph at 0, then the derivative doesn't exist, obviously. But it says if f prime of c exists, then it has to equal 0. Right, so that should be another pretty obvious concept. Alright, so let's see what Rolles' theorem is going to tell us. This says, suppose f is continuous on a closed interval AB, kind of like the previous one, and that it's differentiable everywhere on the open interval AB, so we don't really care about the endpoints. And then here's the other important fact, f of A equals f of B. So our function has to be continuous on the closed interval, differentiable on the open interval, and f of A has to equal f of B. All those things have to be true in order to satisfy the hypothesis of Rolles' theorem. And if those are all true, then for some c between A and B, f prime of c has to equal 0. Alright, so now there's a few cases we should consider before I go into this example. So let me actually do that first. Let's move this down, slide that up. Okay, so let's go through some possibilities. And usually what I would do in class is I would have students come up and try and contradict this. And then that helps you think a little bit more about it. I'm just going to assume A and B are positive, but they don't have to be. Alright, so but A is less than B. So we need to draw a continuous differentiable function, so no sharp points, no cusps on this interval from A to B. And f of A has to equal f of B. So let's say there and there. Okay, so that's f of A, which happens to also be f of B. So they have the same output value, the same y value. Now, the trick is, can you come up here to the board and can you connect those with a continuous differentiable function where you couldn't have f prime of c equal to 0? And so, you can come up and you can try and draw and you can make it look as crazy as you want. Now notice here, on this example, the derivative is 0 there, and there, and there, and there, and maybe at the end. So this theorem is not saying there's only one spot C between A and B, but it's saying there's at least one, there exists one. So this example, there's several values that C could be. There's 4 different values. On the other hand, let's draw another example. So what inevitably always happens is I get a student that comes up and does this. They just draw a straight horizontal segment and say, okay, there's my function f. F of A does equal f of B. It is continuous on the closed interval. It's differentiable on the open interval. Where is C? And then I'd say, well, that's really easy because C can be anywhere. Because every point, if this is a horizontal line, every point on this function here has a derivative equal to 0. So C, there's an infinite number of values for C in that case. So that's what it's saying. But the key is that f of A has to equal f of B. And this theorem, once you get your mind wrapped around this and all the different possibilities and how we could actually prove this, that's used in the proof of the next bigger theorem called the mean value theorem. So let's go ahead now and do the example. And this says, find the value C guaranteed by Rolles' theorem for this cubic function over the interval 1 to 9. Alright, now remember, Rolles' theorem says there's at least one value c. It doesn't say there couldn't be more than one. So what we need to do first is make sure that the hypothesis is satisfied. A lot of times students skip this step. So, is this function continuous on the closed interval 1 to 9? Yes, because it's a polynomial, and we know those are nice, smooth, continuous curves. We also know that it's differentiable everywhere. So the first two parts of the hypothesis are satisfied. The last one we have to check is, does f of 1 actually equal f of 9? Because if the function value at 1 and 9 are not equal, then Rolles' theorem doesn't apply. And usually, it's always going to happen. You won't find a problem that'll say deal with Rolles' theorem where they're not equal, but it is something you should check. I don't know, maybe some crazy teacher would put a problem on a test where f of a doesn't equal f of b, and then students apply Rolles' theorem and it doesn't work. I don't know who would do that. So, f of 1 is going to equal 1 minus 15 plus 59 minus 41. So negative 14, negative 55. I think we get 4 for that, don't we? I'll double check that in a minute. And then f of 9, you plug it in. 9 cubed, yeah, we get 4. I'm just kidding. I should actually check. So let's check. Let's do 9 to the third minus 15 times 9 squared and then plus 59 times 9 minus 41. Sure enough, we get a value of 4. So all the hypothesis of Rolles' theorem is satisfied, so now we're ready to go. So all this is saying is we need to find a point somewhere in the interval from 1 to 9 where the derivative equals 0. So I guess we find the derivative and we set it equal to 0. 3x squared minus 30x plus 59. Set that equal to 0. Alright, so we've got a quadratic. Can it factor? Let's see, 59 is prime. So I think we're going to wind up having to use a quadratic formula. And to save some time, so my video doesn't run forever, let's do this, 3x squared minus 30x plus 59. Enter. And let's go ahead and graph. And you can see that we have 2 zeros here. Second, calculate. Let's go with the first 0. X equals 0 looks good. And x equals 3 looks good. And we get 2.698. So let's say 2.70. So x equals 2.70, and that definitely is within the interval from 1 to 9. And then we check the other one. And sometimes what happens is you can get more zeros, and one or more of the zeros might not be in the interval. So don't just find zeros and say you're done. Make sure that all those answers fall within the interval. And then the next 0, which is also less than 9. Let's see, 1, 2, 3, 4, 5, 6, it's between 7 and 8, actually, it looks like. And so it's 7.309, so 7.31. Now, if we couldn't use a calculator, we would use a quadratic formula, and you'd get the expression, the radical expressions dealing for those. And that's it. So we found actually 2 values guaranteed by Rolles' theorem. Okay, now here's kind of an offshoot of taking some ideas now that we understand and figuring out how to apply here. Prove that this cubic function has exactly 1 root. Alright, So how are we going to handle this? Well, one idea you can do is you can say, let's say, what's f of 1? I know what f of 1 equals. That's easy. Plug it in. 1 plus 3 is 4, plus 6 is 10, plus 1 is 11. Alright? Let me find, how about negative 1? If I plug that in, I'm going to get negative 1 plus 3 minus 6 plus 1. So that's going to give me a negative 3. Now notice, f of, do this over here, draw a little quick graph. F of negative 1 and f of 1. F of negative 1 is negative 3. So just ballpark. And f of 1 is 11 up there. And we know this is a cubic, so it's continuous and differentiable. And we know that no matter what's going on here, we have something like that. Maybe it dips back down below the x-axis, I don't know. So it has to have at least one root. So we know that f of x has some x equals c, where c is between negative 1 and 1, such that f of c equals 0. And we know that by the intermediate value theorem, which says that if a function is continuous on a closed interval, that it takes, closed interval a to b, it takes on all values between f of a and f of b. So somewhere it's got to cross the x-axis for this function. Now I just picked negative 1 and 1 as some random values to check, to find one positive and one negative output. And 1 is an easy number usually to check. Okay, so we know there's at least one root. So now here comes the tricky part. We want to prove exactly one root. So we want to prove that it doesn't have another root. Well, let's say it does. Let's say maybe something like that happened. You know, maybe it has 3 roots. Let's say it has at least another root. So let's assume, I know what happens when we assume that there's some, let's call the first root, well I'll call that c sub 1. Assume there's a c sub 2 such that the function evaluated at c sub 2 equals 0, and also that c sub 2 is greater than c sub 1. So there's another c somewhere along there that crosses the x-axis. Okay. If that's true, let's mark let's mark here c sub 1 and over here c sub 2. And here's negative 1 and positive 1. Okay, so let's do a blue graph. Alright, so here's your 2 roots of your function. Well, wait a minute. Now, f of c sub 1 equals f of c sub 2, and we know it's continuous and differentiable on this interval, because it's a polynomial. So Rolles' theorem actually applies, and that means that there's some other value between c sub 1 and c sub 2. Oops, I didn't mean to draw a point. There's some other value, maybe I should call this x sub 1 and x sub 2. There's some other value where the derivative at that value equals 0. I'll just call this, I don't know, d. So by Rolles' theorem, there exists a d such that f prime of d equals 0. Alright, so now let's go back to our original function and look at f prime. The derivative of this function is 3x squared plus 6x plus 6. The vertex of this function, back from algebra 2, is negative b over 2a. I know this is a parabola that's opening upward. The derivative graph is a parabola opening upward. And x is equal to the opposite of b over 2a, so that would be negative 6 over 2 times a is 6, negative 1. So the vertex of the parabola, which represents the derivative, is at x equals negative 1, and f prime of negative 1, if I plug that in, I get 3 minus 6 plus 6 is equal to 3. So the vertex of the derivative, the parabola which represents the derivative, is at negative 1, 3. And it opens upward. And this is f prime. So where does the derivative equal 0? We're trying to find this point D over here, where the derivative equals 0. But we know, according to our f prime graph, that it never equals 0 because it never crosses the x-axis. It's a parabola and the vertex is above the x-axis. So I know that f prime cannot equal 0, which means that this cannot be true. But everything in the hypothesis of Rolles' theorem was satisfied, so it's supposed to be true. So that leads us back to what we assumed, that there was another 0 of our function f. So that can't be true. And therefore, there is only one place between, and it's between negative 1 and 1, where f of c sub 1 is going to equal 0. So you might have to kind of go through the logic of that again. It was a little complicated. Hopefully I explained it well enough for you, but you might want to go through that again. Now, we're ready for the mean value theorem, but this is already taking quite a bit of time. So what I'm going to do is I'm going to end this as part 1 of the video, and then you can pick up part 2 shortly.